You know the buildings we live and work in every single day? Well, they're hiding a pretty big secret. Turns out, they're massive energy guzzlers, wasting a huge amount of power without us even realizing it. But a powerful new ally is stepping in to solve this invisible crisis: artificial intelligence. Today, we're going to break down how AI is making our buildings smarter and a whole lot more efficient.
So where is all this energy actually going? The answer might surprise you. In a typical office building, get this, a staggering 39% of all energy is eaten up by just one thing: heating, ventilation, and air conditioning, or HVAC. Yeah, that's more than all the lights and all the computers combined. It is by far the single biggest energy hog in the building.
And all that wasted energy comes with a pretty steep environmental price tag. Globally, our buildings are pumping out 2.9 gigatons of CO2 every single year. To put that into perspective for you, that's more than the entire global transportation sector. It's a huge, and honestly, an often overlooked piece of the whole climate puzzle.
All right, so let's dig into this a little deeper. Our building's energy problem. It's really a story about invisible waste that's happening right under our noses. And here's the crucial part. This isn't just about having old, inefficient equipment. The real problem is that these HVAC systems are constantly developing little faults, tiny malfunctions that can go completely unnoticed for months, even years. You know, a valve might not be closing all the way, or a sensor could be just slightly off. These tiny issues add up, forcing the whole system to work way harder than it needs to, which wastes energy and, of course, makes us less comfortable.
So how in the world do you fix a problem you can't even see? Well, what if our buildings had their very own doctor? This brings us to a really cool concept called fault detection and diagnosis. Fault detection and diagnosis, or FDD for short, is pretty much exactly what it sounds like. It's a whole set of methods that use data from a building's sensors to automatically spot when something's going wrong, figure out what's causing it, and then help get the system back to running at peak performance. Seriously, just think of it like an automated health checkup that's running 24/7 in the background. And just ignoring these faults? Wow, that comes at a really high cost. And we're not just talking about higher energy bills. This stuff leads to poor air quality, it makes expensive equipment break down way sooner than it should, and it just creates uncomfortable spaces for everyone inside. And in the worst-case scenarios, an undetected fault, say in a fuel line, could even lead to some pretty serious safety hazards.
Now, there isn't just one way to do this kind of diagnosis. Let's kind of open up the diagnostic toolkit and take a look at the four main approaches for finding these hidden faults.
So you can basically break it down into four main strategies. You've got the classic approaches like physics-based, where you try to build a perfect digital copy of the building. And then there's knowledge-based, which is like following a super detailed rulebook written by human experts. Then you have the modern AI-powered ways, data-driven, which learns right from the sensor data itself, and hybrid, which, you guessed it, mixes the best of all worlds.
Now, those traditional methods, the physics and knowledge-based ones, they're powerful, for sure. But they have one huge drawback. Building a perfect digital model or writing a complete rulebook for just one building is incredibly complex and takes forever. And trying to scale that to thousands of different buildings? Almost impossible. They just don't scale.
And this is exactly where our data-driven detective comes into the picture. This approach uses AI and machine learning to find patterns and weird anomalies in the data that a person, or even one of those fancy physics models, might completely miss.
So how does this detective work? Well, the process is actually elegantly simple, at least on the surface. First, you collect massive streams of data from all the system sensors. Second, you clean up that data, get rid of all the noise. Third, you train an AI model so it learns what normal operation looks like. And finally, you let that model run, and it automatically flags anything that deviates from that normal pattern.
But that's the key question, isn't it? How does a machine actually learn to be a detective? Well, it generally happens in one of two ways.
So with what's called supervised learning, you basically give the AI an answer key. You feed it a bunch of historical data that's already been labeled by humans as either normal or faulty. But with unsupervised learning, you don't give it any labels. You just show it tons and tons of data from a healthy system, and the AI learns the pattern of normal so well that it can instantly spot anything that looks like an odd one out.
And this quote really gets to the core of it. The real power of this data-driven approach is that it finds these purely mathematical links between what goes in and what comes out. It doesn't actually need to understand the physics of heat transfer or know what brand of air conditioner is installed. It just needs the data.
Okay, let's bring this all together. What is the real-world payoff of all this intelligent fault detection? Well, it points us toward a much smarter and much greener future.
The benefits are crystal clear, and they are significant. By catching and fixing these tiny faults early, we see huge energy savings. That directly leads to a major reduction in CO2 emissions. And, at the very same time, we're creating more comfortable, healthier spaces for everyone inside. It's a total win-win-win.
And look, this isn't just some nice-to-have tech. It is absolutely crucial if we're serious about meeting our global climate goals. Organizations like the International Energy Agency have set some really ambitious targets, like cutting building emissions by 40% by 2030. There's just no way we can get there without making all of our existing buildings drastically more efficient.
I mean, the ultimate goal here is to get our buildings to evolve from being these simple static structures into dynamic living systems. We're aiming for buildings that aren't just smart, but are actively responsive and are maybe even capable of self-healing by diagnosing and flagging their own problems.
So let me just leave you with this one final thought. What if our buildings could tell us they were sick before we even felt a single symptom? Before the air gets stuffy or before that massive energy bill shows up?
That right there is the promise of this technology, a future where our buildings work for us and for the planet in the smartest, most efficient way possible.